3.4. Scaling strategies. Horizontal versus vertical, when and why. Growth rarely announces itself. It doesn't show up one day with a label saying scaling problem. It arrives quietly, a few more users, a bit more traffic. A feature becomes popular. A marketing campaign lands better than expected. At first, everything still works, just slightly slower than before. Then one day, something that used to happen only at peak time begins to happen all the time. Background jobs fall behind. Caches stay warm longer than planned. Performance graphs start showing shapes nobody saw before. The team sits down and asks the question that eventually visits every system. Do we make this machine stronger? Or do we add more machines? That question is the heart of scaling. And in practice, almost every approach falls into one of those two families. First, there is the most intuitive answer. Simply make the machine stronger. Add more CPU, add more memory, use faster disks. Move to a bigger instance. It is like upgrading your laptop, the same device, but with more power available. Engineers love this option early on because it is fast and low risk. Nothing in the design changes. You hit restart, the system comes back, and suddenly everything feels lighter again. For a while, this approach feels almost magical. Performance improves, customers stop complaining, graphs flatten out, the team gets to breathe. But there is a quiet rule nobody escapes. Every machine has a ceiling. Eventually, you reach the biggest model your provider offers, or the next upgrade is 10 times more expensive for only a small improvement, or the bottleneck shifts to something hardware alone cannot fix, like a single-threaded process, a locking pattern, or a database under stress. Vertical scaling is wonderful for early wins. It buys you time. It lets architecture remain simple while the product finds its place in the world. But it is not a long-term growth plan. It is a bridge, not the destination. When that bridge starts to shake, teams look at the second path. Instead of making one machine huge, they add more machines and let them share the work. Traffic is distributed. Requests are balanced. One server may fail, but the others continue responding. The system stops being one big box and starts becoming a network of cooperating components. This is horizontal scaling, and it feels powerful, almost limitless. If traffic doubles, add more nodes. If it doubles again, repeat. Big internet companies live here. Streaming platforms, social networks, e-commerce giants, all of them survive because they don't rely on a single heroic server. But horizontal scaling is not free. The moment you split work across multiple machines, new questions appear. Who decides which server gets which request? How do they keep their data consistent? What happens when one node lies about its state? How do you detect failure quickly enough to move traffic away from it? You also discover a new pattern of failure. Machines used to fail individually. Now they can fail in groups. A misconfiguration duplicated across many nodes can create bigger incidents than a single crash ever could. The real mistake many teams make is believing that scaling is automatic, that it simply means traffic increased, add more power. In reality, scaling is first about understanding the real bottleneck. Sometimes CPU is the limit. Sometimes it is the database connection pool. Sometimes it is disk I/O. Sometimes it is latency introduced by a third-party service. Occasionally, one badly written query makes the whole system look slow. Good teams investigate before they react. They let observability guide scaling decisions instead of guesswork. So when does each strategy actually make sense? Vertical scaling works best when the system is still young, the architecture is straightforward, and the bottleneck really is resource-driven. You need a quick fix. Stability matters more than elegance, and redesigning everything would create unnecessary risk. In those moments, a stronger machine is the right answer. Temporarily. Horizontal scaling becomes essential when growth is not a spike, but a pattern, when availability really matters, when one machine represents too much risk, or when different parts of the system grow at different speeds, storage one way, compute another. At that point, architecture shifts from one big brain to many collaborating parts. That shift demands new thinking, Redundancy, replication, graceful degradation, designing with failure as an assumption rather than a surprise. What experienced teams eventually learn is that scaling is rarely an either-or decision. Most systems use both. They scale vertically first, because it is cheap in complexity. Then, when returns begin to diminish, they introduce horizontal scaling gradually, in the places where it gives the most benefit. Not every component needs to be distributed. Not every service deserves a cluster. The healthiest systems evolve instead of exploding into complexity. And scaling is never just about more users. Every scaling choice changes reliability patterns, operating costs, and how engineers debug incidents. A rushed decision can make failures harder to reason about. A thoughtful one can make future crises predictable, sometimes even boring. The real art is knowing when to move from stronger to wider, and designing the system so it can make that transition without breaking itself in the process. In real systems, these scaling ideas are implemented through many different tools. Load balancers such as Nginx or cloud load balancers sit in front of services and decide which server should handle each request. Container platforms like Docker and Kubernetes make it easy to run many copies of the same application and replace them automatically when one fails. Cloud auto-scaling features add new machines when traffic rises and remove them when it falls. Databases scale in different ways. Traditional SQL databases often use read replicas, while systems like MongoDB or Cassandra spread data across many nodes. Caching layers, such as Redis and Memcached, reduce pressure on databases by answering repeated questions from memory. Message queues like Kafka and RabbitMQ decouple components so work can be processed in parallel. We won't dive deeply into each of these tools because they change over time. But they all exist for one simple reason. They turn the concepts we discussed, either a stronger machine or many machines working together, into working production systems. And once we accept that growth introduces new ways things can fail, another question follows. If parts of the system will eventually fail, how do we make sure the whole system doesn't fail with them? That leads straight into the next topic. Fault tolerance and high availability, designing not for perfect machines, but for imperfect reality.